This is Churro. So if you hear a dog barking or just doing various noises in any of my recorded lectures, this is what you can picture. Here he is. All right, so that's Churro. Now let's get on with Chapter 2. Chapter 2 is called An Introduction to Linear Kinematics. So kinematics, remember, is the branch of dynamics or motion concerned with the description of motion. So today we're going to be talking about words and concepts that are used to describe motion, not to cause it, simply to describe it. Okay, so dynamics, mechanics of moving objects, and kinematics specifically, we're talking about describing the motion. So we're going to be using terms you might be familiar with in a general way, such as speed, velocity, acceleration, but today in this lecture you're going to learn the mechanical definition of these terms and how to use them. So in kinematics, like I said, we're describing motion. So what do we need in order to be able to describe motion? First, we need to define space. We need to know where the object starts, where it stops. We also need to know about the time. So how long was the object moving? So motion, we're basically looking to describe a change in position. Okay, and then if we add in the time concept, we're going to be describing how long it took or how quickly the object moved from one position to another. So we need to know these three things. We need to know how long it was moving, where it started, and where it stopped. That's pretty much it. With those three things, we can determine all the other things we're going to be talking about today, which is pretty much what I just said, right? So we're going to be defining position, and we're going to do that with terms called distance and displacement. So those are the two different ways we can describe a change in position. Once we start taking time into account, then we are going to talk about speed and velocity and acceleration. So just to kind of give you the big picture of where we are overall in the course and in this chapter, is we're all the way over there on the left under the kinematic branch of biomechanics. We're talking about linear motion today, and that's the first thing I'm going to go ahead and define to you here in a moment. And then once we understand for sure what linear motion is as compared to angular motion, we're going to talk about linear position, velocity, and acceleration. And of course, later in the semester, we will cover angular kinematics as well. And we'll also be covering linear and angular kinetics. So first, let's get back to linear versus angular motion and give you a definition there. Linear motion, you may also hear the term translational. Just means linear. So this is when motion occurs when all the points on the object move the same distance in the same direction over the same amount of time. The two types of linear motion are rectilinear and curvilinear. And we're going to look at visuals of these in a moment. So just try to take in the language here first, and then we'll look at some pictures. Rectilinear, all points move in a straight line. Curvilinear, all points move along a curved path. So in rectilinear, all points on the body or object move in a straight line. Direction of the object doesn't change, orientation of the object doesn't change, and points on the object move the same distance. So this is when we are either in static equilibrium, certainly there's no change in position, but if you are, let's say you're skating along the ice and holding a position, then that would be rectilinear motion. There's no curve to the movement of your total body. Or you're just on your bike and you're coasting along, you're running on a straight path, straight flat path. All the points on your body as a general being, we're not talking about the joints here, we're just talking about your total body motion, are moving in a straight line. They're all going the same, they're all covering the same distance, they're all going in the same direction, they're all have the same orientation. Curvilinear means that all the points on the body or object still are not, changing direction or changing orientation. and they're all going the same distance, but any point on the object or body, if you follow the path of it, it's a curved path. So again, if you dive off of a rock or a diving board and you just kind of arch into the water, that would be curvilinear motion. A ski jumper going off a jump in the air, they don't keep going straight, right? They curve and come down and land. So again, we're talking about total body motion, not movement at the joints, to describe both of these things. So let's look at some images that'll, I think, make it easier. So here's rectilinear motion. The skier is, I guess that's a skier, a downhill skier. And all the points on the body are moving in the same direction at the same orientation, and they're moving in a straight line. Curvilinear motion, a hang glider here. As the hang glider comes down closer to the earth, the path their body is following is curved. So all the points on the body move along a curved path. Okay, we're not worried about any changes in joint positions here. We're just talking about the overall body position in space. Okay. So when the path of any part of the body can be drawn as over time as a curved line, it's curvilinear. If it's a straight line, it's rectilinear. Now, the other type of motion is angular. So angular motion is when all the points move through the same angle in the same direction over the same amount of time, but different points are going to cover a different amount of, are going to travel a different distance. Meaning, if you think about joint motion is angular motion, or what we also might call rotational motion. So they're all the points are moving about the same angle, or through the same angle about the same point, which is the axis of rotation. So in this picture, the knee joint is the axis of rotation. So you can look at any point on the lower leg, and they're all rotating about the same axis, but the foot will have traveled further than the calf because it's further away from the axis of rotation. So angular motion is anything where there's rotation happening. Okay. So all points are moving through the same angle in the same direction at the same time, but they're going to travel different distances depending how far they are from the axis of rotation. Okay, so this is an example where the axis is within the body, but this can also be true of when the axis is outside the body. So if you're on a swing, your body is rotating about the axis of, let's say it's a tire swing that's attached to a tree branch, that axis of rotation is at the tree branch. So different parts of your body, if they're further away from the tree branch, they will be moving farther than parts of your body that are closer to the tree branch. But they're all moving about the same angle over the same period of time. Okay. Now, throughout that, I kept saying, now I'm not talking about joints, I'm just talking about the body, or vice versa. So really what we typically have with human movement is general motion, which is a combination of the two. What's always occurring at our joints is angular motion. Okay, let me say that again. Angular motion is what's happening at our joints. That's the type of movement that occurs at our joints, which ultimately is what causes us to have total body motion, right? At least from an internal perspective. Angular motion of the joints results in linear motion of the total body. So if we think about if we're walking, the total body motion there, if we're walking on a flat surface, right, is linear. But in order to accomplish that linear motion of walking and moving our body forward, we have to have angular motion at the joints. Okay, here you can see there's angular motion all throughout the joints of this snowboarder. And so that's what's allowing him to change position in the air. So his overall body path would be considered curvilinear, but within that, there's angular motion, not only at the joints, but he's also in rotation in the air. So this would be an example of general motion, meaning there's angular and linear motion happening. The person in the wheelchair, a little simpler example of there's angular motion happening at her probably elbow and wrist and shoulder in order to turn the wheel. So there's also angular motion, of course, happening with a wheel, but that's resulting in general motion, rectilinear motion of the wheelchair and her body in general. Okay, so most movement we look at is general motion. The only time you have true rectilinear or curvilinear motion is if your body literally, there is no joint motion happening. You're just along for the ride, if you will. So if you are in a static position on a skateboard, for example, okay, after you've done the work you needed to do to push off and start your motion, or maybe you just are going down a hill or a slight ramp, if you are standing completely still, then that would be linear motion only. But typically there's going to be movement at the joints causing that linear motion, so it would be considered general motion. All right, so now let's get back to the topic here at hand, linear kinematics. So we're in this chapter, like I said, focusing on linear motion. So we're not going to be talking about joint motion yet. We'll get to that when we talk about angular kinematics. So let's start with defining position. Position is simply an object's location in space. So in this class, we're going to, again, keep things sort of simple here, and we're going to constrain our movement space to be two-dimensional. So since we're in 2D, we need to have an x coordinate and a y coordinate to describe the object's position in space. So if you think about, how we might typically define position, what we're looking at specifically is a change in position. So if you are a runner and you are running from point A to point B, you have two different ways you can describe that. You can say, I ran from my house to the store, and you can measure that either as a straight line distance, meaning literally as we often say, as the crow flies, right? So not exactly how the path you took to get there, but literally just how far apart are those 2 points. Or you can actually measure the entire distance that was covered as you went from your house to the store. Okay, so how far apart those two objects are in the way that you took to get from point A to point B. Okay. And the store versus the house, how do we define the position of each of those? Well, again, it depends on the situation. So typically, if you're running around a track, it's measured, it's fixed, and it's pretty easy to describe how many meters you covered. If you're on a football field, for example, you can also use, the lines on the field. You can say I ran 20 yards from the goal line and I am 15 yards from the left sideline. So you can basically, in some way, shape, or form, we're always using some type of coordinates to figure out where we are in space so that then we can calculate how far we've moved or tell someone what our position is. So the first concept in terms of a change in position is distance. And distance is the measure of the length of the true path that the object traveled. So not just the straight line distance from one point to another, but the true path followed by the object or the person. We're going to use meters as our units here. And what you need to note is that distance is a scalar quantity. It only has magnitude. Because if you look at the example of this sort of wavy line from where the football player starts to where he stops, he traveled 48 yards. That's the distance traveled because it takes into account every little bit of earth that he touched, right? If I started putting positive for the for moving to the right and negative to the left and vice versa and all these things. And then I would end up with a much different number. So we're not taking direction into account. We're just taking into account the total distance traveled by measuring the full length of the path. Okay. So when in football, however, if you think about, first down, second down, the goal for moving down the field in football, that's not taking distance into account, because you can sometimes, in order to gain a yard, you might have run 15 yards if you've had to run to the side and back, and so there are lots of different times and places where different measures of a change in position are relevant. So there isn't one that's better than the other. It's important to know how to use each one, and when it's best to use each one. So let's look at some more examples. If we have a runner that runs 3 blocks north, 2 blocks east, and then 2 blocks south, which is the left picture there, and we ask what is the distance that the runner traveled, we simply add up the number of blocks, right? So they ran 7 blocks. Has nothing to do with how far they went in a straight line path. It has to do with literally the path they followed. On the right there on that map, again, we would need to measure the length of the true path. The length of each of those 3 lines would give us the distance covered by the runner. The second type of change in position measurement we're going to talk about is displacement. So displacement is the straight line from the initial start position to the final end position. These units are in meters as well, but this is a vector. Displacement is a vector. So in order to calculate and report displacement, we need to make sure we include information about direction. So again, if we look at this picture of our football player, the distance traveled was that curved path. The displacement is the straight line path from point A to point B, from the initial position to the final position. Now, in football, this isn't even what's used, right? To get a first down, you need to go 10 yards strictly in a forward position. Angle is not a factor in football. So we don't really use displacement or distance in football. We use sort of a combination of displacement and sort of a straight line version of displacement, okay? So displacement is simply the straight line from the start to the final position, and again, it is a vector. So if we look at our runner again, and they went, the 3 blocks north, 2 blocks east, and 2 blocks south, their displacement is simply the straight line distance from where they started to where they finished. So in the case of this runner and the running around the block, the displacement would be the hypotenuse of the triangle. Okay, so displacement typically ends up being something we have to calculate using the Pythagorean theorem. Same thing for the runner on this map. They ran in this sort of Z-shaped path for their distance, but the displacement is just the straight line from the start line to the finish line. Imagine if you had 2 downhill skiers. They start and finish at the same point, so their displacement is the same. But if the skier that makes wider turns, if one makes much wider turns than the other, they're going to have a wider path. It's going to take them longer probably, but they're going to have a greater distance, even though the 2 skiers would have the same displacement. Actually, before I move to that, let me go back here and point one more thing out about displacement. So there are certain situations in which you would not use displacement. So even though it's a vector and therefore kind of more of a complete answer, as I've mentioned, there are times when it really makes no sense. What about in swimming, where typically you are completing an even number of laps in just about any race? So if a swimmer did a 200-meter swim, that's 8 laps. the finish position is exactly the same as the start position. So if we were to describe swimming races in terms of displacement, every race would be zero, a 0-meter swim. It makes much more sense in swimming to talk about distance, right? Same thing with running around a track. Anytime you might end up in the same place where you started, or it's important to note exactly how much path you covered, you will need to use distance as opposed to displacement. So it's not that one is better than the other. They just have different times and places when they should be used. And in this displacement example here, by the way, the runner, not only would we need to calculate the straight line distance, so that hypotenuse of that triangle, we would also have to say the angle. So since we were given the initial values in terms of north, south, east, and west, if you were to do this math and calculate the hypotenuse and then figure out what that angle is using the length of the sides, you would determine that the runner had a displacement of 2.2 blocks, and it was at an angle of 26.6 degrees north of due east. Okay, so that angle there would be obviously north and of due east. Okay, so you would have to include both of those things for the complete answer. Now, moving to the next topic. Distance versus displacement was the first thing that we used to describe a change in position. Once we start taking time into account, we move into talking about speed and velocity. Speed is distance over time. Velocity is displacement over time. Now, in real life, many of us use these words interchangeably. However, mechanically speaking, speed is a scalar quantity because it uses distance, which is a scalar quantity. Whereas velocity is a vector quantity because it uses displacement, which is a vector quantity. Speed and velocity both are meters per second. Sometimes you might change them to kilometers per hour, depending on what you're describing. And in both cases, you can have an average value, an average speed, or an average velocity. Or you can also look at an instantaneous speed or an instantaneous velocity. So in both cases, what we're looking at here, and I'll tell you a little bit more about average and instantaneous in a moment, is how long it takes for that object to have that change in position. Okay, right? Now we're taking time into account. So how long did it take to have that change in position occur? Now, if we're talking about, let's say, a 100-meter dash, where there's no change in direction as the person runs, and it's simply a straight line, speed and velocity are going to be the same because distance and displacement are the same. Okay, so there are times when these two are exactly the same value. It's true of distance and displacement, therefore it's true of speed and velocity. Anytime we have a change in direction of any kind, then the average speed and the average velocity will be different. Okay. Another thing to point out is if you do change direction as you are moving, so remember our runner example where when they turned and ran east and then they turned and ran south, those are changes in direction, right? So the displacement, therefore, has to take into account that change in direction. So if you change direction, even if your rate of motion doesn't change, if you change direction, your velocity changes. Think about that for a minute. If you are running around a track and you're running at a constant rate of motion, meaning the amount of space you're covering at any given period of time stays constant, that would mean your speed is constant, right? Because speed is not worried about what direction you're traveling. However, as you turn and you go around the corners of the track, and if you run a full lap at a constant velocity, your velocity will, or excuse me, at a constant speed, your velocity will be 0 because you've had no displacement. Or if you run, let's just say you do a half of a lap, okay, you would have to calculate your velocity using displacement as a vector. And because you've changed direction, even if your speed is constant, you will end up with a different value for your average velocity because you've changed direction. So you have to take direction into account. So in certain situations, again, velocity is not the best measure to use. Speed makes more sense. In certain cases, however, velocity is much more accurate. So it just really depends on what you're doing. Again, let me just make that last point one more time. Even if your speed isn't changing, if your direction of motion changes, your velocity changes. Average speed is the distance traveled divided by the time it took to travel that distance. That's typically what we think about when we calculate these values. Same thing with average velocity. Okay, displacement traveled, or displacement of your movement divided by the time it took to achieve that displacement, average velocity. So it's usually over some period of time. Now, instantaneous speed or velocity, this is where if we want to look at what was your max speed or your max velocity during a race or an activity or something like that, or look at a specific point in time when something changed, those would be what we would look at as instantaneous. But if you think about how we calculate speed or velocity, we're taking a distance covered divided by the amount of time it took to cover that distance. So when we think about instantaneous, we really don't have a true way to measure an instantaneous speed or velocity because there has to be some amount of time going by in order for us to do this calculation. So when we think about, a radar gun or something that's supposedly giving us an instantaneous read, it's actually just giving us a read over an extremely small period of time. Okay, so when we take, a split or like a measurement at a specific moment in time, or we look at the overall speeds at different points in the race, those really are things that, even though we consider them instantaneous, they're just basically an average value over a tiny period of time. Okay, so it's the best we can do in terms of instantaneous, but there's really no such thing as truly instantaneous speed or velocity. It has to be measured over some period of time. The better equipment simply can measure things over a shorter period of time, milliseconds. All right, so let's just check in here for a minute. If a swimmer completes a 200-meter swim in an Olympic pool in 110 seconds, which quantity would be better to use to determine how fast she was swimming? Would you use speed or would you use velocity? Hopefully you said speed. In an Olympic pool, a 200-meter swim, as I mentioned, would be 8 laps. So if we were to try to calculate velocity using displacement over time, we would end up with a 0 in our numerator because her displacement is 0. Her start and finish point are at the same spot. We can, however, calculate distance. The distance traveled is 200 meters. So in order to calculate speed, we would just take 200 meters divided by 110 seconds, and that would give us our answer in meters per second for the swimmer's speed. So the answer is you would use speed. Velocity would not give you a valid answer. So if we took our runner 5.5 minutes to run the 7 blocks, and each block was 400 meters, The displacement was 2.2 blocks. Remember where I calculated that. What would be the runner's average speed? And what would be the runner's average velocity? So to calculate the average speed, we would take the distance, which was 7 blocks times 400 meters per block, and divide that by the time it took, which was 5.5 minutes, which comes out to be 330 seconds. Remember, we want to get these to be where we're calculating in meters per second. So 2,800 meters in 330 seconds gave us 8.48 meters per second as the speed. Velocity, using displacement, the displacement was 2.2 blocks, 400 meters per block. Again, divided by the same amount of time. We already calculated that. That's 330 seconds. That answer for the average velocity would be 2.67 meters per second at 26 degrees north of due east. So you can see here, it's extremely important to know what is being calculated when you are given a change of position over time number. Is it speed? Is it velocity? Because they're going to get very different answers depending on what the type of activity is. And the sort of third concept here, we talked about position, we talked about rate of motion. Now we're talking about acceleration, which is the rate of change of rate of motion. Okay? So now we're talking about, is the velocity changing over time? So acceleration is only used with velocity. So it's the change in velocity divided by the time. So again, we can look at average, or we can look at instantaneous, which is truly just a very small time frame for calculation. And it is a vector because we're using velocity, which uses displacement. So we do need to take into account the direction when we're talking about acceleration. So keep that in mind, that negative acceleration can occur in two different scenarios. It can happen when you are slowing down in the positive direction, but it can also happen if you are speeding up in a negative direction. So I'm going to let you think about that for a minute, and I'll show you in a moment how to kind of, a good way to kind of frame that in your brain. Okay. So simply to calculate acceleration, we take a final velocity minus an initial velocity and divide that by the time it took for that velocity to change. So something we always hear about, like, your car can go from 0 to 60 in 7 seconds. Well, those are miles per hour, and so typically we would be looking at this in meters. But if we just kind of do a simple version of this to give you an idea of the concept, what we're talking about here is a change in velocity, 60 miles per hour minus 0 miles per hour, divided by 7 seconds. So what that would give us is that this particular car we're talking about has an acceleration of 8.6 miles per hour per second. Okay. Typically, again, not how we would be talking about it in our class. We'll be using meters per second squared. But just to give you guys a quick example of acceleration, right? It's how quickly can you change speed, or do you change speed in a period of time? But we also have to take direction into account. So let's look at that. Here's one way to kind of think about this, hopefully in your head. The only thing you really need to remember here from a mathematical perspective is if you multiply two positive numbers, you get a positive number. If you multiply a positive and a negative number, you get a negative number. If you multiply two negative numbers, you get a positive, right? So positive times positive gives you positive, and negative times negative gives you positive. Positive times negative always is going to give you negative. And of course, anything times 0 gives you 0. So if we look at somebody who's moving to the right is a positive direction, to the left is a negative direction. So in the first row, the person is speeding up in a positive direction. So the direction's positive and the change in motion is positive. Therefore, the acceleration is positive. Second row, the person is not changing their velocity, meaning their velocity is constant. There's no change in their velocity, and the direction of motion is positive. Therefore, though, there is no acceleration because there's no change in velocity. If the person, on the other hand, is slowing down, but still running in the positive direction, their direction of motion is positive, their change in motion now is negative. They're slowing down. Therefore, their acceleration is negative. That's all pretty simple to understand. What gets a little more confusing for students and even for instructors is when the movement is in the negative direction. So if someone is running and speeding up, but in a negative direction, their direction of motion is negative, their change in motion is positive, therefore their acceleration is negative, based purely on direction in this case. If they are running in a negative direction and their velocity is constant, meaning there's no change in their motion, then of course their acceleration is still zero. It's not a positive or negative zero, right? Zero is just zero. And if someone is moving in a negative direction, so their direction of motion is negative, and they are slowing down, so their change in motion is negative, then we've got a negative times a negative, which gives us a positive acceleration. So just kind of put this image in your brain, and when we're calculating acceleration and thinking about this stuff, use this kind of as a double check to make sure that you are thinking about things correctly and remembering all of your signs for direction as well as change in motion. There's also a self-experiment in your book about this. So here are some values that were calculated. This is Ben Johnson, an Olympic sprinter. And so what is shown here is that he did the 100 meters in 9.79 seconds. So at each 10 meter displacement, we were able to calculate velocity. So what happens is if he did his first 10 meters in 1.83 seconds, then his velocity was 5.86 meters per second, and so on. And then the third column, we simply took the change in velocity and divided it by how much time it took for those measurements. So these were values taken every 10 meters, right? So we were able to capture multiple measurements of velocity and acceleration by not just doing an overall average, but actually calculating an average every 10 meters. Okay, so this is, again, what some people might call an instantaneous velocity or acceleration, because of course these are very small increments of time, but technically still these are averages over, in most cases, about a second. Okay, so velocity in that second column and then acceleration in the third column is where we've taken the change in velocity and divided it by the difference in the time between those two velocity calculations. And what you can see if you just look at that acceleration column, because this is a 100-meter dash, there's no change in direction. So thankfully, our acceleration is pretty easy to understand, because if he is speeding up, it will be positive, and if he's slowing down, it will be negative because there's no change in direction. So he comes out of the block with his greatest acceleration. From there, acceleration actually decreases. He's still accelerating anytime the number is positive. So up through about 60 meters, he is accelerating. He's just accelerating at a slower rate. And then after 60 meters, he's actually decelerating. Okay, and he's decelerating at a greater rate as he reaches the end of the race. So perhaps at about 60 meters, he felt confident that he had the race in the bag, and he didn't need to keep accelerating. So here's a visual of the acceleration of Ben Johnson and Carl Lewis in a race. And this is a plot of their acceleration values at every 10 meters. So what happens here is if you look at the sort of pink boxes, those are Carl Lewis. And if you look at the, I guess, navy diamonds, those are Ben Johnson. And so out of the blocks, Ben had an advantage. And you can see that the displacement values here are a little bit off because we didn't actually calculate our first acceleration value until around 20 meters. So that's why this is off. It's actually kind of 20 through 100 that's shown here. But initially out of the blocks, Ben Johnson had a greater acceleration. Okay, you can see here he stayed positive. Again, if we kind of add 20 to these numbers at the bottom, through about the 60-meter point. And then he had negative acceleration after that. Carl Lewis stayed positive through the same point, but he dipped and went a little more negative around that 70 meters. But then he thought, uh-oh, Ben's ahead of me. And so he tried to go back up to a positive acceleration. Looks like he hit about 0. So he actually held constant as Ben decreased his velocity. So again, there's a lot of different things you can go into each point and figure out who was accelerating more and who was positive and who was negative. And oops, let me go back. At each given point. But what you cannot tell from this type of a graph is who won. You could make a guess based on if somebody had greater acceleration throughout the race, but acceleration doesn't necessarily tell you velocity, right? It's just the change in velocity. So acceleration graphs only kind of give you maybe strategies. Like if it turns out that Ben Johnson lost this race, his coach might say, look, you've got to maintain your acceleration further into the race. After 60 meters, you were decelerating. So that's the kind of thing you can use these values for. But you cannot look at this graph and tell who won the race without knowing the total time it took each runner. So, as kind of a recap for what we've covered, these are the equations for linear kinematics that we've covered so far. We've covered displacement. So displacement and honestly distance. Distance, again, it's sort of harder to write an equation for it because it's the true path. So typically when we're doing calculations, we are talking about displacement. It's the final position minus the initial position. And how we calculate that's going to depend a bit on what the situation is. Sometimes it's simply subtraction. Sometimes it's going to require the Pythagorean theorem. Speed is L over T, so that's the true length or the total distance covered divided by the time it took. Whereas velocity is displacement over time, or if we put in actually the equation for displacement, final position minus initial position, all of that divided by time. And then finally, acceleration is velocity over time, change in velocity over time. So we would take the final velocity minus the initial velocity and divide that by time. So in each case, we're looking at the final value minus the initial value. That'll give us the change in value divided by time for both velocity and acceleration. Okay, so that's the end of part 1 of chapter 2.